Okay, good morning. Last time in our first lecture, we looked at just examples, very simple examples of configuration manifolds. And we saw that certain kinds of things came up. So we had very simple examples where the configuration manifold was Euclidean space. It was R3 in the example, but Rn, let's say. We had examples where the configuration manifold was a circle, which we can think of as being a one-dimensional sphere, if you wish, where an n-dimensional sphere is defined like so. We had examples where the configuration manifold was a product of finitely many copies of circles. That thing has a name. So this is a n-dimensional sphere. And this is an n-dimensional torus. Okay, and it's simply a product of n copies of circles. Okay, and then we had another kind of thing that arose, which was the orthogonal group on 3 dimensions. And you can think of the orthogonal group in arbitrary dimensions. You do that like this. And so these were the kinds of objects which came up when we talked about configuration manifolds for physical systems, okay? And so what we would like to be able to do is we'd like to be able to do calculus on spaces like this. So you can do things like differentiate to talk about, for example, velocity. And at this point, we don't really know how to do calculus on objects like this. So we want to do calculus on these objects. Okay, but at this point, and by at this point, I mean in 280. Okay, where do you do calculus? Will you do calculus on open subsets of Euclidean space? Okay, so multivariable calculus. All right, so we know how to do that, but these things are not open subsets of Euclidean space. That's not an open subset of Euclidean space. In fact, it's a closed subset of Euclidean space. This is a product of n things, neither of which is an open subset of Euclidean space. This is a subset of the n by n matrices, which is in a Euclidean space, but this is not an open subset. It's in fact a closed subset. So you have to devise a way of doing calculus. And the way you do it is kind of obvious. You just leverage what you already know, which is calculus in Euclidean spaces, to be able to work with more general kinds of objects like these. Okay, and the concept for doing that is what's known as a differentiable manifold. Okay, so we'll spend some time quickly kind of blasting through the definition of what a differentiable manifold is, so that we have some tools at hand to talk about these things. Okay, so the idea is that it's a space that looks locally like. All right. Okay, so let's make that clear. So the definition towards what's known as a differentiable manifold just takes a series of steps. And the first step is really just, the way of encoding what locally looks like means. And it looks like this. A chart for a set S is a pair U phi such that U is is a subset of S. Okay. And phi is a mapping from U into Rn. Okay, and it's going to have some very particular properties. Is an injective mapping for which its image is an open subset of Rn. Okay, so there's a picture that goes along with this definition, and it's a picture that's going to show up many times for us as we go along and talk about manifolds. So a manifold I'm going to kind of draw intuitively as a surface of some kind, and that's a good way of thinking about what they are. But a manifold is not by itself a surface, but we can represent it as one in our minds. Okay, so a chart is a simple kind of a thing. We just take a subset U of S, and then I have a mapping phi, which goes down here into Rn, and I have its image, which is open. Okay, so a very simple thing. It's just a bijective mapping from this subset U into some open subset of Rn. Okay, and that's what this means. Okay. All right, so that's step one of the construction. Step two of the construction is what happens if I choose another chart. Okay, so I want to choose some other chart like so, and maybe maybe it's over here and it doesn't overlap this one, in which case it's kind of not problematic, but maybe it does. And you can think of phi is labeling points in U by points in Rn, and so you're going to have kind of two potentially different labelings for these overlapping regions, and you want to have some notion at hand about how to do that in the right way. Okay. And first to do that, let's introduce a simple kind of piece of terminology just coming from multivariable calculus. So a mapping phi into from U into V. And what are U and V? So U and V are both open subsets of some Euclidean space. So U is an open subset of Rn, let's say, and V is an open subset of, let's say, Rm. We'll see that for this definition, it actually turns out that n must be equal to m. Okay, so such a mapping like this is a smooth diffeomorphism. If phi is of class C infinity. Okay. Okay, so class C infinity, of course, means it's infinitely differentiable. And as a synonym for infinitely differentiable, we'll use the word smooth. So whenever I say smooth, I always mean infinitely differentiable. Okay, so you could say this is a C infinity diffeomorphism, a smooth diffeomorphism, just as you wish. Okay. So V is invertible, okay, so it's a bijection from U into V, and therefore it has an inverse. And I'm going to ask that its inverse also be of class C infinity. Okay, and so it's not true that 1 and 2 implies 3. Okay, and there's simple examples that you'll see on your homework. Okay, so it turns out, and you kind of know this, so in fact this mapping is not just smooth. Of course if it's smooth, it's continuous. And so what I have is I have a continuous mapping between open subsets of Euclidean space whose inverse is also continuous. So it's not hard to believe that it must necessarily be the case then that n is equal to m. It's in the C0 case for continuous mappings, that's actually not easy to prove. It's easier to prove in the C1 or certainly in the C infinity case. But in any case, I'm just going to say it must therefore be the case that n equals m. Okay. All right. Okay, so now we're ready for kind of step 2 of our definition of manifold. And so again, the idea is I'm going to consider 2 charts, and I'm going to ask when they overlap, must there be some kind of compatibility condition between the overlaps? Okay. All right, so let S be a set with 2 charts, U phi and V psi, such that U intersect V is not empty. Okay. If they are empty, then there's nothing. The definition I'm going to give is vacuous. Okay, so the charts satisfy what's called the overlap condition. And you also might say, or they're compatible. Say either thing, probably lots of other things. Compatible, compatible if, okay, so some conditions must be met. So first condition is that if I take my map phi and I apply it to the intersection, or if I take psi and I apply it to the intersection. Okay, so each of these, therefore, so phi maps into some Euclidean space, as does psi. And so I'm going to require that both of these be open subsets of whatever Euclidean space they take values in. Okay, and then the other condition is that the overlap map and the overlap map. So there's going to be a picture that goes along with this. So we'll see what this thing means. But it's psi composed with phi inverse from. Okay, so it maps from phi of U intersect V into psi of u intersect v. Okay, now both of these things by hypothesis from part one are open subsets of Euclidean space, and I'm going to ask that this map be a C infinity, be a smooth diffeomorphism. Okay. And so, you know, the idea is that I have these two ways of labeling the same set of points on my set S, and the same set of points is where these two charts overlap, and the means of labeling these things are going to be consistent, and consistent means exactly this: that when you go from one representation to the other one by this overlap map, that's a smooth diffeomorphism. Okay. All right. Okay, so that's what a chart is. All right. Now, what we want to work towards is we want to work towards doing this around every point in our set S, and so it's obvious how you're going to do that. You're going to cover S with charts, and you're going to require that all of those charts satisfy the overlap condition. Okay, and the resulting thing that you get when you do that is, has the school well, 1980s school geography terminology, a collection of charts that covers some region in which you're interested is called an atlas. So we still have a set S is a family A. Okay, so it's a bunch of charts. All right, and so these charts are labeled, indexed by some set A, and I make no restrictions on A. A can be finite, countable, uncountable. Okay, so any arbitrary collection of charts. So it's a family of charts such that S is the union of the chart domains. Okay, so they have to cover S. And if I take two charts labeled by different, possibly different symbols A and B, then UA, VA, and UB, VB satisfy, are compatible. Okay, so they satisfy the overlap condition. Okay. And so notice, this is really only interesting in the case where they intersect. If they don't intersect, then the overlap condition is satisfied vacuously. So that's what an atlas is. Okay. All right, so now we're getting close to something, right? So we have this set S, we cover it with charts, okay? And each chart gives us a representation of some subset of our set S as an open subset of Euclidean space. And we do this in such a way that whenever two of these representations overlap or intersect, then they're compatible in a very precise way, okay? Now there arises the possible difficulty of the following scenario, that I come along, we have the same set S, and I come along and I choose an atlas for S, so I cover it with charts, okay? And my charts all satisfy the overlap condition with respect to one another, Okay, now you might come along for the same set S, and you might cover the set S with charts, form your own atlas, and your own atlas is internally consistent. So any two charts in your atlas are compatible. It can be the case, and there'll be homework problems where you can easily construct situations where those two atlases are not themselves compatible with one another. Okay, and so what you need in order to guarantee that you and I are doing something which is consistent is we need for your charts and my charts to satisfy the compatibility condition or the overlap condition. Okay, and what that does is that gives you an equivalence relation on the set of atlases, right? So two atlases are equivalent when their charts are compatible with one another. And there's a very slick way of sort of saying that their charts are compatible with each other, and it's like this. Atlases A1 and A2 for a set S are compatible, or sorry, are equivalent if their union is an atlas. Okay. All right, and so if you parse that simple expression that their union is an atlas, it just says exactly what we need to be the case, which is that charts from here are compatible with charts from here. Okay. All right, so then finally, a differentiable manifold is a pair S, I'm going to write it as D, where S is a set and D is an equivalence class of atlases on S. Okay. And so the way you build a differentiable manifold in practice is you build an atlas. Okay. And then once you've built an atlas, then, you know, by definition, you've built the equivalence class, which contains that atlas. And so that's how you put together your manifold. And so by choosing an atlas, you don't just choose the atlas, you choose an equivalence class of atlases. So all other atlases which, you know, have this property. Okay. So let's see how this works with a couple elementary examples. Okay, so let's take an open subset of Rn. Okay, so this is a very simple example of a manifold, and it's a very dull one. Okay, so this is a different, and so just I will use different language for the same thing here. This is very standard kind of terminology. Okay, and so an open subset of Euclidean space is a smooth manifold. All right, and so again, to make something into a manifold, all I need to do is choose an atlas. Well, there's an obvious atlas here, which is just set U itself with the inclusion mapping into Euclidean space. So the image of the inclusion mapping is U itself, which is open, and so there's an obvious chart, and that chart covers all of U. So to summarize that, okay, so it has an atlas consisting of a single chart. That's not typical. Okay. Let me now look at another simple example, but one which has enough going on that it actually illustrates a little bit better than the open subset of Euclidean space, how the manifold construction works. Okay, so I'm going to take S1. To be the circle. Okay, and I'm going to turn that into a manifold, and I'll do that in kind of the obvious way. All right, or at least it sort of starts out, and then you have to kind of kludge it in order to actually satisfy all the proper definitions of a manifold. Okay, so there's kind of an obvious chart for S1. So if S1 looks like this, okay. Well, there's kind of the angle chart, right? So there's many kinds of ways you can measure the angle chart. So the way I'm going to do it here is I'm going to measure. I'm going to measure the angle like so. And I'm going to call that theta, and I'm going to call it theta 1 because I'll have to have a theta 2 later on. Okay. And so now, so I need to make that into a chart. Okay, so that's the intuition. The chart, well, how am I going to measure theta? Well, let's take sort of the maximal range for theta. So it's going to go from pi here, coming along this way, to minus pi there. Okay. And so what that means is in order for the chart map, as we're going to see, to map into an open subset of Euclidean space, it turns out what that means is I have to omit that point. Okay, so I'm going to take U1, my chart domain, to be S1, take away the point, minus 1, 0. Okay, and then I'm going to take phi1 to be the angle coordinate that I've just located here, that I've just called here theta 1. Okay, now of course you want to just say that theta 1 is the inverse tangent of y over x, right? The problem with that construction is that that's only valid between minus pi over 2 and pi over 2. To really have this be defined for angles between minus pi and pi, you have to not use just the normal inverse tangent function. You have to use this kind of a what I would call a smart tangent function, which I write as a tan. And it's a function of 2 arguments, not just y over x. And all it does is it just returns that angle. Okay, so you could define it using inverse tangents. Your definition is going to have to, change as you go from here to here, and then you'll have to have a special definition for the y-axis. So let's just summarize that discussion. We'll say we have this function, which I call a tan, which is a function of these two arguments. Okay. All right. So is this a chart? Well, to check the definition of chart means, well, certainly it's a subset of S1. So it should be an injective mapping onto an open subset of some Euclidean space. Okay. So the Euclidean space here evidently is R1. Okay. So phi1 of U1. So I need to check that it's an open subset of R1, but my construction is that this is the interval minus pi to pi. Okay. And this is open. Okay. And it's a bijection, clearly. So to every angle, so it's a bijection onto this set. Clearly, to every point in the interval minus pi to pi, there's going to be a unique point on the circle, except for that point, which maps into the interval minus pi to pi. Okay, so it is indeed a chart. Okay, now this chart does not cover S1 because it omits that point. So according to my definition of manifold, I need to find another chart. Okay, and my other chart is going to be U2 is going to be S1, take away 1, 0. Okay, so now I'm going to kind of do my chart kind of going the other way. All right, so I'm going to omit that point. And then the angle that I'm going to define it like so. So I'm going to take a point here, and I'm going to measure a positive angle like that. That's going to be my theta 2. Okay. And so if I take if I take this point, which is xy, theta 2 is also equal to theta 1 for the point minus x minus y. Okay, so phi 2 of x, y is a tan of minus x minus y. Okay, so this is also a chart. Okay, because I go from minus pi to pi. Okay, so now I have possibly an atlas. Okay, certainly it covers S1, but what I need is for it to satisfy these two charts to satisfy the compatibility condition. Okay, so what do I need to do? So I need to check that these two subsets of R1 are open. Okay, and then I need to determine the overlap map and show that it's a smooth diffeomorphism. All right, so let's do that. Okay, so phi 1 of U1 intersect U2. Okay, so for phi 1, so for For U1, I remove this point, and for U2, I remove this point. And so when I take the image of U1 under, U1 intersect U2, I'm going to take the angles minus the angle for that point, which is pi, and the angle for this point, which is 0. Okay. Point is that this is minus pi 0 union 0 pi. Okay, and similarly for the other angle chart. Okay, so those are open. Then I have to calculate the overlap map. Okay, so this is annoying, but let's go ahead and do it. Phi 2 composed with phi 1 inverse. Okay, so what I'm going to do is I'm going to, when I write down this overlap map, what I'm really doing is I'm writing the angle theta 2 in terms of the angle theta 1. Okay, so this will be a function of the scalar angle variable theta 1. Okay, and there's going to be a couple cases that I have to keep track of. Okay. All right, so I'm writing theta 2 in terms of theta 1. All right, so let's first look at what's happening down here when theta 1 is between minus pi and 0. Okay, so first I'm going to consider the case where theta 1 is in minus pi 0, and then I'm going to consider the case where theta 1 is in 0 pi. Okay. All right. So again, I'm expressing theta 2 as a function of theta 1. Okay. So here's a point down here with its angle theta 2. What I want to do is I want to say, okay, how do I express theta 2 as a function of this angle, which is theta 1? Right. Okay. So it's going to be, so here, theta 2, the way I've measured theta 2 is that this is a positive angle, and this angle for theta 1 is negative. So it's going to be, if you think about it for a minute, let me write something down, then I'll ask myself if it's correct. So it should be minus pi plus theta 2, right? So as when theta 2 is equal to 0, so it's minus pi, and then as theta 2 increases, then because theta 2 is positive here, then I'm increasing theta 1 to 0 there. Okay, so I think that's right. And then the other situation is when theta 2 is in this hemisphere. Okay, and so theta 2 here is negative, theta 1 is positive, and so this should be, therefore, pi minus theta 2, right? So when theta 2 is 0, theta 1, sorry, when theta 1 is pi, theta 2 is 0, which is correct. And then when theta 1 is 0, theta 2 is, whoops. So, oh, I'm sorry. Let me just make sure I have this right. Okay, so I'm writing theta 2 as a function of theta 1. So here, when theta 1 is, yeah, sorry, I have this backwards. I wrote the other overlap map, sorry. Okay, so this one is going to be, let's see if I got the signs right. So when theta 1 is minus pi, theta 2 is 0, which is correct. And then when theta 1 is 0, theta 2 is pi. Okay, that's good. So sorry, let me do this one now. So I have an angle here, which is theta 2. So theta 1 goes, when theta 1 is pi, theta 2 is 0. And then when theta 1 is 0, theta 2 is minus pi. So it should be, if I have this right, it should be minus pi. And so yeah, minus pi minus theta, right? So when theta is equal to pi, it's 0. And when theta is equal to 0, it's minus pi. Okay, so theta 1. Okay, good. Sorry. Okay, good. So, so what we need is we need for that map, okay, to be, according to the definition, a smooth diffeomorphism. Okay, so let's plot it. Okay, so from pi minus pi minus pi. Okay, so it has kind of two segments. So I'm plotting here theta 1, theta 2. And so when on this segment, I go from theta 1 is equal to 0, it goes from pi down like this. Okay, and then when here it goes theta 1 is 0, it's minus pi, so it goes like this. Okay. Now, the question then is this a smooth, is this smooth? Okay, so for it to be diffeomorphism, you have to calculate its inverse, but to calculate its inverse, you just kind of do a similar sort of a calculation. Okay, so is this thing smooth? Well, it's important to remember that these points are not included in the domain of the function, because you look at that function and you say, well, it's obviously not smooth, it's not even differentiable, but it is differentiable because the discontinuity is not included in the domain of the function. So the function is only defined from here to here and here to here. And certainly on each of these open intervals, it's smooth. In fact, it's linear. Okay. Okay, and then similarly, phi1 composed with phi2 inverse of theta 2 is also smooth. Okay, and this is, of course, the inverse of this one. Okay, so that's an example where we kind of laboriously went through by hand and showed that this thing is a manifold. Typically, you don't do that. And what we'll see next time is that for many manifolds of interest, there are more indirect and satisfying ways of showing that something is a manifold. But we'll get to that next time.